In our previous module 3, we have learned about the mathematical proofs of the linear system when the eigenvalues are both real and negative, and when the eigenvalues are real but of opposite signs. In this module 4, we will look into the stability about the equilibrium point of a generalized nonlinear system. Here we consider the stability of the equilibrium solution of a nonlinear system of the form dx dt is equal to Ax plus Gx, where the nonlinear part Gx is equal to the n component matrix G1, G2 dot dot Gn is weak in comparison to x, and G1x divided by maximum of norm x1 norm x2 dot dot norm xn comma G2x divided by maximum of norm x1 norm x2 dot dot norm xn dot 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 Gnx divided by maximum of norm x1 norm x2 dot dot norm xn are continuous functions of x1 x2 dot dot xn and vanishes for x1 is equal to x2 dot 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 is equal to xn equal to 0. If G0 is equal to 0, then xt equal to 0 is an equilibrium solution of 1, and such a system is called a weakly nonlinear system. Stability of every solution for weakly nonlinear system may not be possible, but stability of equilibrium solution may be discussed in some cases with the help of stability of zero solution of linearized problem. The following theorem is useful in this regard. So, the theorem says, suppose that the vector valued function gx divided by norm x is equal to gx by maximum of norm x1 norm x2 dot 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 norm xn is a continuous function of x1 x2 dot dot xn which vanishes for x equal to 0, then number A, the equilibrium solution xt equivalent to 0 of 1 is asymptotically stable if the equilibrium solution xt equal to 0 of the linearized equation x dot equal to Ax is asymptotically stable. Equivalently, the solution xt equal to 0 of 1 is asymptotically stable if all the eigenvalues of A have negative real part. Number B, the equilibrium solution xt equal to 0 of 1 is unstable if at least one eigenvalue of A have positive real part. And number C, the stability of the equilibrium solution xt equal to 0 of 1 cannot be determined from the stability of the equilibrium solution xt equal to 0 of x dot equal to Ax if all the eigenvalues of A have real part less or equal to 0, but at least one eigenvalue of A has 0 real part. Please recall the asymptotically stability definition. It means that the system has to be stable and the path should approach the equilibrium point. The proof is as follows. We use the variation of parameter formula and we say any solution xt of 1 can be written in the form xt is equal to e to the power at x0 plus integration 0 to t e to the power a t minus s g x s ds given by equation number 2. We want to show that norm of xt tends to 0 as t tends to infinity. Now, we know that if all the eigenvalues of A have negative real part, then we can find positive constant k and alpha such that norm of e to the power at x 0 is less or equal to k times e to the power minus alpha t norm of x 0, and norm of e to the power a t minus s g x s is less or equal to k times e to the power minus alpha t minus s norm of g x s. Moreover, we can find a positive constant sigma such that norm of g x is less or equal to alpha by 2k norm of x if norm of x is less or equal to sigma. It follows from our assumption that g x by norm x is continuous and vanishes at x equal to 0. Consequently, equation 1 implies norm of x t is less or equal to norm of e to the power a t x 0 plus integration 0 to t norm of e to the power a t minus s g x s ds, which is less or equal to k e to the power minus alpha t norm of x 0 plus alpha by 2 integration 0 to t e to the power minus alpha t minus s norm of x s ds, as long as norm of x s is less or equal to sigma and 0 less or equal to s less or equal to t. By multiplying both sides by e to the power alpha t, we get e to the power alpha t norm of x t is less or equal to k times norm of x 0 plus alpha by 2 integration 0 to t e to the power alpha s norm of x s ds. This inequality can be simplified by setting z t is equal to e to the power alpha t norm of x t. For then z t is less or equal to k times norm of x 0 plus alpha by 2 integration 0 to t z s ds. We see that norm of x t is equal to e to the power minus alpha t norm of z t, which is less or equal to e to the power minus alpha t k times norm of x 0 plus u t, which is less or equal to k times norm of x 0 e to the power minus alpha t by 2, as long as norm of x s is less or equal to sigma, 0 less or equal to s less or equal to t, or if norm of x 0 is less or equal to sigma by k, then the above inequality gives norm of x t is less or equal to sigma for all future time t. Consequently, this inequality is true for all t greater or equal to 0 if norm of x 0 is less or equal to sigma by k. Finally, we observe that norm of x t is less or equal to k times x 0 and norm of x t tends to 0 as t tends to infinity. Therefore, we conclude that the equilibrium solution x t equivalent to 0 of 1 is asymptotically stable. For part B, since the proof is quite lengthy and beyond the scope, we will skip the proof. And for the part C, we take two examples which will clear the theorem. We will present two differential equations of the form 1, where the nonlinear term Gx determines the stability of the equilibrium solution xt equivalent to 0. We first consider the system of differential equation dx1 dt is equal to x2 minus x1 times x1 square plus x2 square, and dx2 dt is equal to minus x1 minus x2 times x1 square plus x2 square given by 3. The linearized equation is of the form ddt of x1 x2 is equal to 0 1 minus 1 0 x1 x2, and this is obtained by taking the linearized part from these two equations, where we neglect the nonlinear part for the time being, and hence this equation can be written in the form dx1 dt is equal to 0 dot x1 plus 1 dot x2, and this can be written as dx2 dt is equal to minus 1 x1 plus 0 dot x2, and in matrix form we get in the form d dt of x1 x2 equal to 0 1 minus 1 0 into x1 x2. The eigenvalue of this matrix can be easily calculated, that is, we consider the equation determinant of A minus lambda I is equal to 0, and if you do that, the characteristic equation will be given as 0 minus lambda 1 minus 1 0 minus lambda equal to 0, and if you expand, you will be getting lambda square plus 1 equal to 0, which means lambda square equal to minus 1, and which means lambda equal to plus minus I. Since the eigenvalues are plus minus I, we can conclude that the linearized system will give a focus or spiral point which is asymptotically stable. Now, to analyze the behavior of the nonlinear system 3, we multiply the first equation by x1 and the second equation by x2, and we add, and this gives x1 dx1 dt plus x2 dx2 dt, which is equal to minus x1 square into x1 square plus x2 square minus x2 square into x1 square plus x2 square, and which can be written in the form minus of x1 square plus x2 square whole square. But x1 dx1 dt and x2 dx2 dt is equal to half of ddt of x1 square plus x2 square. Hence, ddt of x1 square plus x2 square is equal to minus 2 times x1 square plus x2 square whole square, and this implies x1 square t plus x2 square t is equal to c by 1 plus 2 ct, where c is equal to x1 square 0 plus x2 square 0. Thus, we see that x1 square t plus x2 square t tends to 0 as t tends to infinity for any solution x1 t x2 t of 3. Please note this expression: as t becomes large or t tends to infinity, the right hand side becomes 0, and this is what has been told here, that is, as t tends to plus infinity, x1 square plus x2 square tends to 0 for any solution x1 t and x2 t of 3. The value of x1 square and x plus x2 square at any time t is always less than its value equal to 0, and therefore, we conclude that x1 t equal to 0 and x2 t equal to 0 is asymptotically stable. On the other hand, you consider the system of differential equation of the form dx1 dt is equal to x2 plus x1 into x1 square plus x2 square, and dx2 dt is equal to minus x1 minus x2 into x1 square plus x2 square, given by equation 4. Like before, we consider the linearized system here in the form x dot is equal to 0 1 minus 1 0 into x. In this case, ddt of x1 square plus x2 square is equal to 2 times x1 square plus x2 square whole square, and this implies x1 square t plus x2 square t, which is equal to c by 1 minus 2 c t, where c is equal to x1 0 square plus x2 0 square. Please notice that every solution x1 t and x2 t of 4 with x1 square 0 plus x2 square 0 is not equal to 0 approaches infinite in finite time, and this happens because the denominator is 1 minus 2 c t. So, if we consider t equal to 1 by 2 c, then this becomes undefined. So, as t tending to 1 by 2 c, the right hand side becomes plus infinite, and therefore, we conclude that the equilibrium solution x1 t is equal to 0 comma x2 t equal to 0 is unstable. Theorem 0.1 is also useful in determining the stability of equilibrium solutions of arbitrary autonomous differential equations. Let x0 be an equilibrium value of the differential equation x dot equal to fx given by equation 5, and we set zt equal to xt minus x0. Then z dot is equal to x dot, which is equal to f of x0 plus z given by equation 6. Clearly, zt equal to 0 is an equilibrium solution of 6, and the stability of xt equal to x0 is equivalent to the stability of zt equal to 0. We have just learned about the stability about the equilibrium point of a generalized nonlinear system. We will now look into an important lemma which will give us an algorithm to find the stability of the equilibrium point. Let fx have two continuous partial derivatives with respect to each of its variables x1, x2 dot dot xn. Then f of x0 plus z can be written in the form f of x0 plus z is equal to f x0 plus az plus gz given by equation 7, where gz divided by maximum of norm of z1 comma norm of z2 dot dot norm of zn is a continuous function of z which vanishes for z equal to 0. Theorem 0.1 and lemma 1 provide us the following useful algorithm for determining the stability of an equilibrium solution xt equivalent to x0 of x dot equal to fx. We first set z equal to x minus x0, and then we write f of x0 plus z in the form az plus gz, where gz is a vector valued polynomial in z1, z2 dot dot zn, following with the terms of order 2 or more, and the matrix A is given as the following Jacobian matrix A as del f1 del x1 at the point x0, del f1 del x2 at the point x0 dot 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 del f1 del xn at the point x0, and likewise del fn del x1 del fn del x2 dot dot del fn del xn, all these at the point x0. Next we compute the eigenvalues of A. If all the eigenvalues of A have negative real part, then xt equal to x0 is asymptotically stable. If one eigenvalue of A has positive real part, then xt is equal to x0 is unstable. So, what we are doing here, we are giving a small perturbation to the system, and once you get that perturbation, we expand this function f in Taylor series and only retain the linear part, which is written in the form az plus gz. Basically, this gz is the nonlinear part, and in the linear stability analysis, we consider this Jacobian matrix A, and we conclude that if all the eigenvalues of A have negative real part, then the system is asymptotically stable, otherwise it is unstable. We now look into an example where we have to find all equilibrium solutions of the system of differential equation dx dt is equal to 1 minus xy and dy dt is equal to x minus y cube, given by equation 8, and we have to see whether this system is stable or unstable. Now, to find the equilibrium solution where both x and y are constants, we have to put dx dt is equal to 0 and dy dt is equal to 0, and this will give 1 minus xy equal to 0 and x minus y cube equal to 0. Next, we can substitute x equal to y cube in this equation, and if you solve, you will get x equal to 1, y equal to 1 and x equal to minus 1, y equal to minus 1. And therefore, the two equilibrium solutions of 8 are 1 1 and minus 1 minus 1. For stability of the first equilibrium solution 1 1, we proceed as follows. We set u equal to x minus 1 and v equal to y minus 1, and then du dt, which is equal to dx dt, equal to minus u minus v minus uv, and dv dt is equal to dy dt, which is equal to u minus 3v minus 3v square minus v cube, and we rewrite the system in the matrix form. ddt of uv is equal to minus 1 minus 1 1 minus 3 uv minus the nonlinear part uv 3v square plus v cube. The Jacobian matrix minus 1 minus 1 1 minus 3 has a single eigenvalue at lambda equal to minus 2, and hence we conclude that the equilibrium solution xt equal to 1 and yt equal to 1 of 8 is asymptotically stable. For the stability of the second equilibrium point minus 1 minus 1, we set u equal to x plus 1 and v equal to y plus 1. Then du dt is equal to dx dt, which is equal to u plus v minus uv, and dv dt is equal to dy dt is equal to u minus 3v plus 3v square minus v cube. Rewriting again the system in matrix form, we will get ddt of uv is equal to 1 1 1 minus 3 into uv minus the nonlinear part minus uv 3v square minus v cube. The eigenvalue of the Jacobian matrix 1 1 1 minus 3 is minus 1 minus root 5, which is negative, and minus 1 plus root 5, which is positive, and hence we conclude that the equilibrium solution x t equal to -1 and y t equal to -1 of 8 is unstable. Summing up, in this chapter, which consists of 4 modules, we have learned about the qualitative behavior of the differential equation, both linear as well as nonlinear. We have learned about the phase portrait of node, focus, saddle point and center. And at the end, we have learned about the stability of the equilibrium points of the generalized nonlinear case, and I hope it is understandable to you. Thank you.